Okay. So, remember how I said that typically we write our equation, a differential equation, as the derivative is equal to something. But the intention is that we actually want p is equal to something over here. Okay? So that's kind of the goal of these differential equations. Yeah? To solve them, we want to get this. And because these are so complex, what they tend to do is they tend to give you what the answer is, and then you need to show that. Just like we did here. Just a word of caution though, typically we do see a lot of fudging here, right? Because you guys have the answer. So just be aware that if you are going to make some algebraic jumps, like don't make any leaps that don't make sense. Like for example, at this step here, if you genuinely can't see how to get from here to here, don't do some like pretend operation that doesn't make sense. I guess like you just kind of take your chances and you just write the next line and hope that the marker is convinced enough that you do know what you're talking about. That's something that a friend actually showed me, that you just kind of, in desperate times, what you can do is you just stop where you got up to and you just try and work backwards from like the answer and see how far you can get. But the thing you should not do is just write something that doesn't make sense and then get there, okay? So don't write anything that's incorrect, because that really takes away the legitimacy of your proof, right? So what we're trying to do is we're trying to get this. And remember, James already told us that we need to integrate. But what I was saying is that the integration of something with an addition is easier than the integration of a product, okay? So even if you can't get this proof out, just recognize that this is the side you want to integrate because it's an easier thing to do, okay? So we can start off with the fact that dp dt is equal to this thing. So just to confirm, what James and Matt realized is that what you have is this. So this is dp dt, but what you've shown is something slightly different. It's the reciprocal of that. Yeah. So in order to do that, we take the reciprocal of both sides now. So dt dp is equal to 1 on this, right? And then we can say that, yeah, this is the same as that. Yeah, that's right. So dt dp is equal to this guy here. Good spot. Now, before I go ahead and do the process, right, remember integration is going to be a key part of this. But remember some like other tricks that we've been using. Like if I'm looking at this, we already have an idea that this is going to be some kind of logarithm. But remember, we can combine logs using some algebraic manipulation, and then eventually when we get up to exponentials, we can also remove the constants by treating them as coefficients. So that's things you need to be thinking about before you get into this, otherwise it can be a bit overwhelming. So just kind of have that in the back of your mind, right? Okay, so let's go ahead and integrate now. So remember, the integration process, I guess the way that we kind of write it out is that I want to integrate both sides, but then like we need something to integrate with respect to. So that's why we kind of split up this fraction in a way, and we put it like that. We can multiply both sides by dp, right? And so this left-hand side is going to be t is equal to something. Now this constant, again, with constants, what I might do is I might just take that constant out. So I'll put it outside the whole integral. That just makes my integration a bit easier. This one's going to be nice, yeah? This is just 1 on p. I already have the derivative of this denominator on the numerator, yeah? So that's just your basic kind of log. That's just ln of p. This one, though, not as nice, right? Think about why, because we not only do we have a constant here, that typically doesn't change things, but you have a negative p, and the derivative of that is -1. So in order to address that kind of manipulation, we want a -1 here, but then what do I have to do to the outside of this whole thing? I have to also, because I've changed the expression now, right? So I have to make this a subtraction, right? Because the whole thing should be plus 1 in 1,000 minus p, but when you have the manipulation done in this way, what it means is that you can now integrate this as a logarithm, and it will be just minus now because I've changed this operation, minus ln of 1000 minus p, and don't forget your constants there, okay? Oh, and I need 5 and 12, so that's what happens when you skip steps. You just like forget things. Now, remember, what's the goal of this? The goal of this is to get P as the subject. So just kind of have that in the back of your mind. We want P as the subject. Also, keep in the back of your mind is that we have initial conditions, right? We know that initially, at t equals 0, or at the beginning, there's going to be 250 fish. So you also want to be careful about when you use that information. You could use it here, but is it going to be like super obvious what it's going to be? I don't know, potentially. You have to do a bit of rearranging and stuff like that. But what you might want to do is you might want to rearrange it a little bit more first before you use that information. Because the whole goal is we're going to have to show that P is equal to this. So we know at some point we are going to have to get P is equal to something. Okay? So we want to think about what manipulations we can actually do first. Think about the logs. The logs is the first place we can look to do something, right? Is there anything I can do with those logs? I've got subtraction of logs at the moment. Anyone remember their log laws? Yeah? Subtractions become a division. So t is equal to 5 on 12 outside of ln, and then these two are going to be divided by each other. Now, technically, with the absolute values, they seem a little pedantic, but they're meant to be left there until we can know for certain that the other side is positive. So we kind of have to keep them there out of just notation until we can conclusively say that. Okay? Other things we're trying to do here, I guess I can move the constant to the other side. So I can do like t minus c is equal to that. So let's keep going. Other things we can do. We want to remember ultimately get p is equal to something, right? So let's get rid of this bracket thing so that I can, should be absolute values here. Let's get rid of this bracket so I can start doing stuff with it. We'll multiply both sides by the reciprocal. So 12 on 5 outside of t minus c. Just multiply both sides by 12 and 5 to get rid of that there. We can think about dividing it by that, right? I want to start freeing up these p values because ultimately in the answer here I don't have a log. And they kind of give you a big clue about what to do, right? We've got an exponential here. So if you remember, exponentials and logs are inverse operations. So if I raise both sides to the power e, then I can remove that log. So e to the 12 on 5 outside of t minus c. And then when you raise this to the base e, you get this. Is that what you did, Harry?
Yeah.
Nice.
We still need the absolute.
Yeah, it's a good question. Do we still need the absolute? Think about like what the exponential graphs can look like, right? When we change these variables. So at this point, I'm happy for you to recognize that this whole thing should be positive. If you think about like what your exponential graphs can look like, they either look like that or like that, depending on what you're doing there, right? So at this point, I'm happy to get rid of them. Now, as we keep going, I guess something that they tend to do, remember, is that they don't like to have exponentials like this. They much prefer to have exponentials in this way. They actually split them up, right? Because remember, this is just minus 12 on 5c. But then this you can think of as these two powers subtracted. So they tend to write it like this, as a second exponential there, yeah. And the reason why they do that is because what it allows you to do, it allows you to get a coefficient, right? Because right now, this is not just e to the power something. It's actually e with a coefficient in the front. And you can see how this is all kind of falling into place. If you put 12 and 5 in the calculator, you are going to get 2.4, right? So you can start to see like little snippets of where you need to end up. But we also need a coefficient in the front. So what they tend to do at this point to here, which is not immediately obvious, it's not like, oh, I would know how to, like, that makes sense. Like, you just got to be aware of, oh, they tend to split it up in that way to bring out the coefficient. So we can let this just be some value, like a, for example. Cool, so let's say that's a e to the 12 on 5t is equal to p on 1000 minus p. And so like the constant that you're trying to find now has kind of been replaced by this a value, yeah? So what we can then do is that instead of finding c, we're trying to find the a. And this is a situation where now you can actually easily use this information. Here, right? Here, like you could have done it and still found a value, but here it's much clearer now, right? Because at t equals to 0 and p is equal to 250, what are you going to get? Well, you're going to get a times e to the power 0, right? Because that whole thing's 0 here, the whole power is 0, and it's equal to 250 on 1000 minus 250. And what's that going to give me? One on. One on 3. Okay, cool. That's our constant. So now we've got 1 on 3. E to the 12 on 5t is equal to p on 1000 minus p. Okay? So we're close. We're pretty close, right? And just kind of to push you in the right direction again, just realize that p is meant to be the subject. And you can start to see parts of what we want. Like we want this 2.4 thing. We want a 3 there. And we've got like little bits of that, but it's just not quite right at the moment. We still need to do a few extra steps here. I guess the annoying thing is that we've got like these p's here, and they're kind of separated by a fraction. So I guess we can kind of do something about that. We can multiply both sides by 1000 minus p, I guess. Is that going to be the best thing to do? It's like the only thing we can do, so let's just do it. So we've got 1 on 3 e to the 12 on 5t outside of 1000 minus p. I guess we could actually multiply both sides by 3 here now to get rid of this fraction here, and that can be kind of where your 3 comes in, I guess. So you can do a few different things here. One thing you can do is you can expand, okay? You can also divide by this, I guess, and just see where it ends up. Any preferences?
Expanding is easier than dividing, but I don't remember if you're doing that.
I don't know. That doesn't make sense.
Sorry?
I did something different.
Okay. To either, what did you do?
Like, you know, back when you like rearrange like that, I found C while it wasn't in that.
Okay, sure. And then what did you do?
There's just a lot of algebra to get to the end. That's just a lot.
James, preference on expanding or?
Probably expanding.
Let's try it. Let's see what happens when you expand. So we've got 1000 e to the 12 on 5t minus p e to the 12 on 5t equals to 3p. And what you notice is that then these two you can group together now. So, isn't this side here? Yeah, so yeah. Well, like we can you can actually have them on the same side now without the fraction here, right? So we've got 3p plus p e to the 12 and 5t. And what that means is now that these p's are in common, so you can actually factorize these out. So we've got...
Yeah, that's after the...
Yeah, sorry, yeah, you're right. So,
Confused my words.
just randomly disappearing e's. Okay, cool. Let's factorize this out here. So I haven't done anything here yet. Factorize out the p here.
My robot got my fix off.
Yeah, so I mean, when you divide by this, because the whole goal is to get p as a subject, and we're very close, right? We just divide by this expression here, right? So I'll just do it at the top here. So we're going to get 1000 e to the 12 on 5t all over this. That's equal to p. And then what did you say, Matt, that you wanted to do?
Bring the top p down to the bottom, and then it becomes negative 12 on 5t, and then you multiply by the 3, and then by the positive 1 becomes 1.
Yeah, so you kind of do the same thing as you did last time when you, remember how we had like that thing on the numerator which we didn't want? We had that 5,000. So I guess here you could do the same thing. You divide both sides, the top and bottom, by the 12 on 5t.
Programs use the index all though.
What's it, as in bringing this guy down? Or?
Yeah, bringing it down sort of thing, because then it becomes negative.
Yeah, so you can do, so if you do it this way, what's going to happen is that these will go away, right? That just goes away. That becomes 1. Then this becomes, yeah, so it becomes 1,000 over 3 divided by this plus 1. But then remember, e to the 12 and 5t, because that's on the denominator, it's on the bottom of a fraction, we can rewrite it as the negative. So remember, like 1 on x is the same as x to the negative 1. Right, that's the idea behind that one. So one last step. We write it as a negative.
Wasn't that only B?
Sorry?
That was only B, wasn't it?
Yeah.
C and D.
C and D, I'll let you do for homework. We'll go through tomorrow. Okay. Sorry, a lot of algebraic work there at the end, but we got there. So, good stuff.